Hello and good morning, guys. So today we're going to be discussing, we're going to be using Notability in order to discuss our first online video, which is going to be about a topic that we discussed in class before, but it's of great importance, so that's why I felt the need to reiterate this topic. It's about the relationships between the graph of f of x, f prime of x, and f double prime of x. Before I move on, I have to remind you of what is f prime of x, and basically f prime of x is the derivative function, and the derivative function represents the slope of a given point. So we're going to be looking at different cases for f of x and how those. So that f double prime of x is the second derivative, which means the relationship that f of x has with f prime is the same as the relationship that f prime has with f double prime. Not so much talking after this. We're going to be writing everything we're going to say, so don't panic. This is going to be a nice online video. So for f of x, first of all, case number one, if f of x was an increasing function, then any increasing function, you draw a tangent to that increasing function, and the slope of the tangent is going to be positive, and that tells me straight away that f prime of x is positive. I don't know anything about f double prime. The second idea, if f of x was decreasing, then for a decreasing function, its slope is negative, f double prime. We don't have any information regarding that. It could be anything. The first piece of analysis is when f of x is actually concave up. And if f of x is concave up, we need to track the tangent. If we track the tangent, we can track f prime of x. So if we draw a tangent at this point, and then you draw a tangent at this point, let's say, you draw a tangent at this point, and then you draw a tangent at that point. What you notice about the tangents is that the first tangent I drew has a very negative slope, became less negative, became zero, became positive. Conclusion is the slope is increasing. How can I say that? Because the slope went from very negative to less negative to zero to positive. So the behavior is that the slope is increasing. And if the slope is increasing, means the first derivative is increasing, means the second derivative, which has the same relationship with the first derivative as the relation between f and f prime. So you see the relation here with f and f prime. This will copy there. So it's going to be greater than zero. The fourth condition that we're going to be talking about today is concave downwards. If the function is concave downwards, similarly, you would notice if you draw the tangents, they're gonna decrease in slope. The tangents are gonna decrease in slope, maybe. Okay. So the tangents are gonna go from positive to less positive to zero to negative. So it means that the slope of the tangent is gonna decrease. And again, I'm gonna be copying some piece of information that I've written in the beginning, this thingy in blue. So it's going to be copied there. So it's going to be less than zero. Okay. This is condition number 4. What about condition number 5? Condition number 5 is that f of x has a minimum. If f of x has a minimum, then as you noticed in the previous graphs, I'm going to highlight that in green so that I don't draw it again, that the tangent is horizontal. And that means that the first derivative is 0. You also noticed that the function is concave upwards. For if you have a min, then the function is concave upwards. And the relationship is if the first derivative, if the function is concave upwards, then the second derivative is positive. That's the first conclusion. Or the fifth conclusion. The sixth conclusion, if f of x has a max. Again, as you notice from this graph, let me highlight it in pink. If it has a max, then the tangent is going to be horizontal. The slope of the tangent is going to be 0 again. Since it's concave downwards, then the second derivative is going to be less than 0. So, those two thingies together, represent what we call the second derivative test. We use it in optimization, if you remember. And the idea of the second derivative test is that if a function has an extrema, and the extrema can be a min, a max, or a point of inflection. So, let's say we want to find if f of x has a max/min. We say that f of x is equal to f prime of x is equal to 0. But then how do you know if it's a max or a min? You do the second derivative test. If the second derivative came out positive, then the function has a min. And if the second derivative came out negative, then the function has a max. So we move on to the last idea. Point of inflection. The point of inflection, we said it appears in more than one way. So the first kind of point of inflection, I'm going to mark it in red now, is the point of inflection by definition is the point where the function changes concavity. So if you notice, before this point and after this point, what actually happened? Before the point of inflection, the function was concave down. And if it's a concave down, then the first derivative, as we can infer from before, is decreasing. After the point of inflection, the function was concave up, and concave up, as you noticed here, means the function is gonna increase. Then what corresponds to the point of inflection? Decreasing, then increasing, means we have a minimum in here. And if the function has a minimum, then its first derivative, as you can see this relationship here, is going to be 0. So in this case, the first derivative has minimum, it means the second derivative is equal to 0. But it's very essential to say that it changes sign. It changes sign from what to what? In this case, because the first derivative is decreasing, so it's from negative to positive. Okay. Last condition. The other point of inflection. Again, I'm going to mark it in red in there. So, again, it's the point of inflection is going to split the graph into two. The first part of the graph is concave up. Concave up means the derivative is increasing. After the point of inflection, the function is concave down. It means the first derivative is decreasing. In between them, we have a max. Again, if the function has a max, its derivative will be equal to 0. Again, it has to change sign. So it changes sign. This time it's going to change sign from positive to negative. And changing the sign, please put a star on this. I mean, you don't need to put a star, I'll put the star for you. Changing the sign is a very essential condition in determining a point of inflection. So sometimes we just say, okay, prove that it has a point of inflection, and then you just tell me that the second derivative is equal to 0. Yes, that's the most apparent test. But if the second derivative doesn't change sign, then we don't have a point of inflection in our hands. Put that in mind, very important point. This must be one of your dreams. Okay, last point before I finalize this video is gonna be about something that rarely shows in exams, but it's of worth mentioning. Okay, which is the point of inflection where both derivatives, the first and the second, must be zero. As you notice, this point of inflection, if I draw a tangent, its slope is going to be zero. And since it's a point of inflection, then the second derivative is also going to be zero. It happens with functions like x cubed, x to the power 5, x to the power 7. All right, that concludes our video. We're going to have some practice exercises on class kick to make sure that you get this idea. See you.